On the left side of this split screen is a centralized database. On the right is a decentralized ledger. Both systems store data, but they operate on divergent architectural models. Traditional databases optimize for raw speed and flexibility. They rely on a central administrative authority who holds full permissions to create, read, update, and delete information, a structure known as CRUD. A blockchain explicitly rejects that trust model. It functions strictly as an append-only state machine. Data can be added, but once an entry is confirmed, historical modifications and deletions are impossible. To see how this resilience actually works, we have to pull the system apart, examining it as a multi-layered stack from basic cryptography all the way up to modular rollups. By distributing the ledger across a massive global network, the architecture eliminates the single point of failure entirely. Data integrity relies on converging cryptographic proofs, replacing the need to trust an institutional reputation. The foundation of the stack is the cryptographic data layer. Look at this visual representation of the SHA-256 algorithm. A block of text goes in, and a fixed-length hexadecimal string comes out. This is a deterministic process. The exact same input always yields the exact same output. But watch what happens when we change just one character of the input. The output completely scrambles. This is known as the avalanche effect. Zooming out to look at an 80-byte block header, you'll find a specific 32-byte field called the previous block hash. This field contains the hashed output of the preceding block's header, creating a rigid mathematical link connecting the current state to the past. If an attacker tries to alter a record in the past, the avalanche effect immediately changes the hash of that old block. That breaks the pointer in the subsequent block and every block after it. To hide the tamper, the attacker would have to recompute the hashes of all subsequent blocks faster than the rest of the network combined. Securing the blocks themselves is only half the problem. The network also needs to verify who is interacting with the data without relying on a central registrar. It does this using the elliptic curve digital signature algorithm, or ECDSA, specifically relying on the SEC-P256K1 curve. Users hash their transaction data and sign it using a private key. The network then takes the user's public key to authenticate that signature. Because the underlying math works in only one direction, it proves the account owner authorized the action, enforcing strict non-repudiation. By pairing deterministic hashing with elliptic curve signatures, the network fully replaces the database administrator with an interconnected chain of immutable proofs. Once a transaction is cryptographically signed, it needs to reach the rest of the global system. This happens at the network layer, which operates over a decentralized peer-to-peer topology with no central routing servers. This node map shows the gossip protocol in action, a technique based on epidemic spreading. A single node receives new data and sends it to a very small, random subset of its connected peers. Those peers then forward the data to their own random neighbors. By relying on exponential spreading rather than broadcasting to everyone at once, the system avoids massive communication overhead. In a network of 25,000 nodes, it typically takes only about 15 rounds of gossip for a piece of information to saturate the entire network. This rapid dissemination introduces a specific vulnerability. What happens if malicious or Byzantine nodes attempt to flood the network with fake transactions during the gossip process? Because every valid message carries an ECDSA digital signature, receiving nodes can instantly verify the authenticity of the data. If a node gossips an unsigned or fraudulent transaction, its peers immediately drop the data and blacklist the offending node. These gossip protocols guarantee what engineers call eventual consistency. Within seconds, the entire global network possesses an identical pool of pending transactions, ready for the next phase of validation. Now that the nodes share the same pending data, they must agree on the exact sequence to record those transactions. Coordinating this agreement among anonymous, untrusted actors is a variation of the Byzantine generals problem. This quadrant chart maps the consensus layer, showing how different network environments require specific fault tolerance models to establish a single source of truth. Proof of work secures permissionless environments. Miners compete to brute force a random nonce until their block's hash falls below the strict difficulty target. It provides security by tethering the ledger to physical energy expenditure, though it limits transaction throughput. Proof of stake replaces computational effort with economic capital. Validators lock up native tokens to earn the right to attest to new blocks. If they behave maliciously, the protocol automatically penalizes them by slashing their staked tokens. For closed enterprise consortiums, practical Byzantine fault tolerance uses a rigorous three-phase voting process among known participants. It operates efficiently as long as fewer than one-third of the nodes act maliciously. In strictly trusted enterprise environments, the Raft protocol offers extremely fast finality. It assumes all actors are honest and only protects against hardware crashes, offering crash fault tolerance rather than Byzantine security. A distributed ledger's choice of consensus algorithm dictates exactly how it balances decentralization, operational security, and total transaction throughput. Moving to the top of the stack, we reach the application layer. This is where the ledger evolves from a static record of balances into a platform for programmable logic via smart contracts. This flow illustrates the Ethereum Virtual Machine, or EVM. High-level code compiles down into low-level opcodes that feed directly into a decentralized, stack-based environment. The EVM uses a 256-bit word size, specifically engineered to process complex cryptographic operations efficiently. Allowing anyone to deploy arbitrary code introduces a severe vulnerability known in computer science as the halting problem. A poorly written loop could theoretically run forever, locking up the nodes and freezing the entire network. To solve the halting problem, the network relies on a strict resource pricing mechanism called gas. Every single opcode the EVM executes carries a specific computational cost, measured in units of gas. Users pay for this gas via a transaction fee, which splits into two parts: a base fee dictated by network congestion that gets permanently burned from circulation, and a priority fee that acts as a tip to the consensus validator. If a transaction hits a complex loop and depletes its gas limit mid-execution, the network triggers a failsafe. All state changes are instantly reverted to protect the ledger, but the user still forfeits their fee to pay the validators for the computation performed. The EVM provides a Turing-complete environment for decentralized logic, while enforcing rigid economic consequences to ensure no single contract can abuse the shared network. The architecture we just built is entirely functional, but as a monolithic system, it faces a hard limit. Requiring every node to execute every single transaction on the EVM caps the network's total throughput to the speed of an individual node. This pillar represents the monolithic model, handling all operations in one place. The modern engineering solution unbundles this stack into a modular architecture, breaking the system into specialized execution, settlement, and consensus strata. By moving the execution layer off-chain, secondary networks can process thousands of state changes independently, using technologies like zero-knowledge rollups. Zero-knowledge proofs rely on advanced cryptography to verify complex operations without revealing the underlying data. The rollup bundles hundreds of transactions and generates one succinct validity proof, sending only that proof down to the base layer. Meanwhile, a dedicated data availability, or DA layer, ensures that the raw transaction data remains published and accessible to anyone. This guarantees transparency without forcing every consensus node to execute the heavy computational logic. Unbundling heavy computation from root layer consensus resolves the traditional limits of distributed systems, allowing massive scale while retaining root layer cryptographic security. Distributed ledgers have evolved from rigid databases into unbundled, high-throughput modular state machines. The entire structure relies on a precise sequence of technical layers. ECDSA secures user identity, SHA 256 guarantees historical integrity, P2P gossip enables global synchronization, and Byzantine algorithms enforce universal consensus. When you measure this stack against a traditional CRUD database, the shift in accountability is total. Instead of relying on administrative oversight, the system provides an immutable, math-based history where errors and corrections are visible forever. As zero-knowledge proofs and modular scaling remove barriers of privacy and speed, the network maintains high-volume datasets without sacrificing decentralized security. The design of a blockchain strips away the need for central authority. It engineers a single shared reality where the integrity of the state is guaranteed entirely by mathematics, rather than institutional decree.